Salam and welcome everyone. So today we're going to be working on the question on the screen that says estimate the freezing point of 200 centimeter cube of water to which 2.5 grams of NaCl has been added. Treat the solution as ideal. So when you look at this question, you see that we have a freezing point question where we're told to determine the freezing point of 200 centimeter cube of water to which 2.5 grams of NaCl has been added. Treat the solution as ideal. This question is from chapter 5 of the Atkins Physical Chemistry 11th edition. This is question 4b. And we're basically told to determine the freezing point, okay, of 200 centimeter cube of water. So we have the volume of water to be 200 centimeter cube, to which 2.5 grams of NaCl. We have the mass, okay, of NaCl to be 2.5 grams. So we're also told to treat the solution as ideal. So what this is telling you is that they want us to determine the freezing point of 200 centimeter cube of water to which 2.5 grams of NaCl has been added. So in this case, we have to determine the freezing point of water after a mixture has occurred, which is a mixture of NaCl and waters. Now, this question is also from chapter 5 where we're dealing with simple mixtures and mixtures in ideal solutions and all of that. So the next thing we have to do is to determine the formula that we're supposed to use. As you can see, this is a question that involves us using freezing point. The keyword here is freezing point, so we're going to be using the freezing point equation, or also known as the freezing point depression formula, which is just simply changing T sub F is equal to K sub F multiplied by B, where the change in T sub F is the change in freezing point, or change in freezing point. So what this is just simply telling us is that before before mixing, the solvent, in this case the solvent is water, has its own freezing point, so it has its own temperature. And then after mixing, this new solution, which is the solution of NaCl and water, basically salt water, would have a different freezing point. And freezing point is just basically the temperature in which a solvent or a solution freezes. So that's basically it. So the change in freezing point is just the difference between the temperature before mixture and the temperature after mixture. So the temperature of the pure water as and the temperature of the water salt solution. So the difference between them is just simply the change in freezing points. Then you have K sub F, which is just simply the freezing points constant for the solvent. Okay. And then lastly, B is just simply the molality of the solute. Now, to explain this further, remember what I just said. The change in T sub F is equal to K sub F is equal to K sub F multiplied by B. This is what you call the freezing point equation. Or you can also call it the freezing point depression formula, or freezing point depression formula. For some of you, depending on what your syllabus was in your own university or in high school, you would have been taught this formula. So there's the boiling point elevation, which you're going to be dealing with the boiling point, and there's the freezing point depression, which you're going to be dealing with the freezing point. So that's just basically what is going on here. Now, if you look at K sub F, we're told the freezing point constant for the solvent, and then B, the molality of the solute. K sub F is a constant value, just like we're aware that the speed of light is a constant value. The value for gravity is a constant, or acceleration due to gravity is a constant value. We know Avogadro's number is a constant value, right? So freezing point constant is just a unique and exact value for a particular solvent. And in this case, our solvent, in this case, is water, okay? And our solute is NaCl, also known as table salt. So that's what's basically going on here. Let me rewrite it up here again. We have our NaCl is the solute, because this is very important as we work. And then water is the solvent. So yeah, that is the next thing we have to do. Now I've explained changing T sub F and K sub F. Now the last thing we have to explain is the molality. And molality is just simply, the formula is the moles of solute, or number of moles of solute, okay, divided by the mass of the solvent in kilograms. So therefore, the unit for molality is usually mole per kilogram, where the numerator is the number of moles of solute divided by the kilogram of the solvent. So we go back to our question. We see that we're not given the number of moles of solute. We don't have that. We don't have the mass of the solvent. We do not have the value for B. The only thing we do have is actually K sub F, and that's because we know that it's a constant value. And you can Google it to determine the freezing point constant for water. You can, when you Google it, you find out that the freezing point constant for water is just simply 1.86 Kelvin kilogram per mole. But I want to quickly mention something, right? This is a K sub F of the solvent, and in this case, K sub F of water. And this is the value. You don't always have to Google it. The Atkins Physical Chemistry 11th edition textbook has resource section at the back of the textbook, and this value is actually there, 1.86 Kelvin kilogram per mole. So now we have to determine what the molality of the solute is, and then we multiply it by the KF to at least find the change in freezing point, since that's what we're going to be looking for using this formula. So we have a situation here. We don't have the molality, we don't have the moles of solute, we don't have the mass of solvent. But if we remember, we have the mass of the solute given to us, right? From the previous way, we have the mass of NaCl, which is just 2.5 grams of NaCl, okay? And we also have the volume, okay, of water, which is just simply 200 centimeter cube. That was what were given to us. But now we have to determine the number of moles of solute and the mass of solvent in kilograms. So now, even though this is what we have, we can use our knowledge of general chemistry, right? General chemistry knowledge is telling us that we're told to determine the number of moles of solute, so the number of moles of NaCl, but we have the mass and we know the identity of the solute, which is NaCl. So therefore, we can simply determine the number of moles based on what we have. So the number of moles of NaCl is just simply going to be the mass of NaCl, okay, divided by the molar mass of NaCl. So what that would look like will simply be the number of moles of NaCl, okay, simply going to be the mass, which is just simply 2.5 grams, divided by the molar mass of NaCl, which is 58.44 gram per mole. So how I got the molar mass of NaCl is just simply by Googling it, but it's just basically you adding the atomic mass of Na plus the atomic mass of Cl, or the molar mass of Na plus the molar mass of Cl. When you add them up, this is what you get, 58.44 gram per mole. I don't feel like I have to write out each one of the steps. Whenever you're doing advanced chemistry courses like thermodynamics, all of those like little bit of steps are not as important as you actually just getting the message, because NaCl is general chemistry stuff. You can literally Google it and you just do. You don't really need to show the solution to determine what the molar mass of NaCl is. But if you wish to do it in your own personal notes because it helps you to study, please feel free to do so. I'm just not doing it because I don't think it's like 100% necessary. But yes, the molar mass of NaCl is 58.44 gram per mole. So 2.5 grams divided by 58.44 was just simply 0.042778919 mole. Okay, and of course we cancel out the grams here and cancel out the grams here. 1/1 over mole is just going to give you mole. So we have successfully determined the number of moles of NaCl. Now that means we have the mole of solute, half of the values that we need to determine the molality is done. Now we have to determine the mass of the solvent water. So let me use a different color. So we are given the volume of water to be 200 centimeter cube, but we're told to determine the mass of water in kilograms, which we're not given. Now, again, if you remember from your Gen Chem, you would remember that anytime you're given volume and you're supposed to get to mass, or you have mass and you're supposed to get the volume, you can determine one or the other using something called density. So, in this case, in order for us to go from volume of water to mass of water, we're going to have to utilize the parameter density. So, therefore, remember, density is just simply mass over volume. And since we're dealing with mass, we can just constant multiply and have mass is equal to density times volume. Now, of course, this is not just mass, this is mass of water, okay, is equal to the density of water multiplied by the volume of water. So we're given the volume of water. We know that to be 200 centimeter cube, but then we need to know what the density of water is. And I have to quickly explain something to you guys. A lot of you may be thinking, okay, the density of water, yeah, isn't it is just this, and that. I want to be very careful, and I want to tell you guys this is because it's key to solving this question. Remember this question, put it in your mind that we're dealing with the freezing point of water. What this is telling you is that we're dealing with values at the freezing point temperature of water. So we're actually going to be using the density of water at 0 degrees Celsius. So now the density of water, okay, of water, H2O, at 0 degrees Celsius is simply 0.99984 gram per cm cube. And the reason why I wanted to explain this is because a lot of students are used to having questions where the temperature is always at room temperature, so 298.15 Kelvin or 25 degrees Celsius. But the issue with that is in this particular case, we're dealing with the density of water at 0 degrees Celsius, like around that. And the reason why I have to mention this is because the density of water changes with temperature. So meaning the density of water at 25 degrees is different from the density of water at 0 degrees, and is also different from the density of water at 15 degrees, 20 degrees. Anytime there's a change in temperature, expect the density of water to change. So that's why the reason why I'm very specific. So we have the density of water at 0 degrees Celsius. So the mass of water, okay, is simply going to be the density of water at 0 degrees Celsius, which is just 0.99984 gram per cm cube, okay, multiplied by the volume of water, which is just simply 200 centimeter cube. Cancel out the centimeter cube, cancel out the centimeter cube. So the mass of water is simply 0.99984 times 200 centimeter cube. We ended up with 199.968 grams. So this is the mass of water. Now remember, the question says to have the mass of water in kilograms. So what that would look like would be we're going to go from grams to kilograms, which is simply divide by 1000. So that's basically what that is. So the mass, okay, of water in kilograms is simply just going to be 199.968 times 10 raised to the power of negative 3 kilograms, or we can just simply say 0.199968 kilograms. So this is basically what this is. So if we go back to our equation, determining the molality, we see that not only have we found the moles of solute, we've also found the mass of the solvent. And yeah, our work is being done properly. So yeah, if you're enjoying this video so far, please make sure to give it a like. I do really work hard in all my videos, and my goal is to help you guys as much as possible. So we have the formula changing T sub F is equal to K sub F multiplied by B, or changing T sub F, okay? In this case, it's simply K sub F, okay? Remember, this is for the solvent, so K for F of water, multiplied by the value for B, which is just the number of moles of NaCl, okay? Remember what I said, molality is number of moles of solute divided by the mass in kilogram of solvent. So divided by mass of water, okay, in kilograms. So yeah, that's it. So of course, we already know what to do. Changing T sub F is equal to K sub F is just 1.86 Kelvin kilogram per mole, okay, multiplied by the number of moles of NaCl, 0.04277891 mole. So I'm just going to put that down. 0.04277891 mole, okay, divided by the mass in kilogram of solvent, which is just simply 0.199984 19969 kilograms. So of course we're gonna cancel out the like units, cancel out the mole here, kilogram here, and kilogram here. So we end up with change in T sub F is just simply 1.86 Kelvin multiplied by 0.04277891 divided by 0.199968 will just simply give you 0.213926684. So yeah, changing T sub F is just simply going to be 1.86 multiplied by 0.213926684, and you end up getting 0.397903632 Kelvin. So this is simply the value or the answer to the change in T sub F. Now you're going to be wondering, yay, we've answered the question. Yes, we are almost done, but our work is still not done. We still have one more thing that I need to explain to you guys. The question does not ask us to determine the change in temperature or change in the freezing point value. The actual question is telling us to determine the temperature of the freezing point after mixing has occurred. So before I explain anything further, I have to go on to show you the concept behind this question and then to help you bring light into what you're supposed to do at the very end. So first of all, let me draw the container, okay, before, and then the same container after. So this first container is before mixing, okay, and then this one is after mixing. In the first container before mixing, what we actually have is just pure water, okay, at 0 degrees Celsius. So of course, maybe you have some ice there, okay, but mainly water. So it's just pure water. Then we have the addition of 2.5 grams of NaCl, and what you end up with here is salt water. So you have NaCl plus water. So, okay, we have maybe some ice still. Now, the reason why it's very important for you to know what's going on here is that um your work is basically explaining to you that what they want you to determine now is the temperature of the solution after mixing. This is the temperature of the solution before mixing. And the reason why it's very important for you to know this is that this equation at the beginning I told you was freezing point equation, and some people call it freezing point depression formula. It is important for you to know that any solvent that is used before mixing is pure, right? In this case, pure water is water that does not contain any impurities or any form of solute. So before mixing, what we have here is actually a solvent, pure solvent. Um, it contains no solute. At this particular case, the temperature is going to have its own unique freezing point value. It's just like in the case of pure benzene as a solvent, pure naphthalene as a solvent, pure anything as a solvent. In that particular case, if there is no mixing that has occurred, meaning there is no solute, it is pure and is going to have a definite temperature. But then mixing occurs with something, and this thing, NaCl, even though we're calling it salt water, NaCl per water, basically causes this thing to not just become pure solvent anymore, but becomes a solution. And a solution, anytime a solvent goes from solvent to solution, the temperature is going to decrease, meaning the temperature, okay, that occurs before mixing, okay, is always going to be greater than the temperature of freezing point temperature after, okay, mixing. So what this is telling you is there's something called freezing point depression. It is called freezing point depression for a reason. Solvent, pure, has its own definite temperature. When you start mixing solutes with it, basically contaminates it, it loses its purity. Hence, it's going to have a decrease in temperature of its freezing point. So expect that whatever we have here, which is here T, F after is going to actually be less than the freezing point of water before mixing. So basically, T sub F after is what we're told to solve for. And I apologize if it sounds like I'm rambling. I'm really trying to explain the concept to you because you need that knowledge to be able to go on to do the final answer. So T sub F after is just simply going to be T sub F before, okay, mixing, minus the change in T, which is just the difference in the value for the freezing point before and after mixing. So yeah, so that is it. So T sub F after is simply just going to be the temperature before mixing. Remember, I just explained it to you in the diagram that the temperature of a pure value, the freezing point temperature of a pure solvent is unique. In this case, it's unique because it is unique, right? In this case, we're dealing with water, and the freezing point of water is just 0 degrees Celsius. And of course, 0 degrees Celsius in Kelvin, which is what we need to solve this question, is just 273.15 Kelvin minus whatever the value for changing T sub F is, which we calculated to be 0.397903632 Kelvin. So I'm going to write that down. So 0.39790362362 Kelvin. And of course, we put that in our calculator. The T sub F after is simply just going to be 273.15 minus 0.397903632 Kelvin, which is just simply 272.7520964 Kelvin. So that's basically the answer to this question. And of course, we're scientists, we have to put our work in the proper number of significant figures. And as you can see, we have this in two decimal places here, and then two decimal places. We don't significant figures if we're dealing with multiplication, decimal places if we're dealing with addition or subtraction. Again, significant figures if you're dealing with multiplication or division. In this case, we're dealing with subtraction, so two decimal places, and we end up with the temperature um after mixing for the freezing point is just simply 272.75 Kelvin. And this is basically the answer to this question. If you have any questions, suggestions, concerns, please put it in the comment section. I'm here to help you. If you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, college, or university, I'm the tutor for you. I help students succeed in all their STEM related courses and be the best version of themselves in academia. So if you love the way I tutor or mentor on my videos, please do not hesitate to email me at shohabitutoring@gmail.com. I'll be expecting your email. Assalamu alaikum wa rahmatullahi wa barakatuh.